So first of all, it's an expression that can be written. A polynomial, remember, is an expression that can be written with our variables x raised to a power. Now, these powers cannot be fractions. They cannot be negative. They have to be integers. They have to be positive whole numbers in order to be classified as a polynomial. So n, which is your power, is a non-negative integer. When I say integer, I'm talking about a whole number, no decimals, no fractions. X is the variable, and each number in front of x is a coefficient. Remember, a variable cannot stand alone. It will have a coefficient. Remind me again, if there's no number written in front of the x, what is the coefficient? 1. All right? And it is called a leading coefficient for a sub n. Remember, the leading coefficient is the number in front of the variable with the highest power. If you have a term that does not have a variable in it, remember we call that the constant term. So remember, the constant term is the term that has no letter with it. Okay? So just to review, some things that make an expression a polynomial. All of your exponents have to be whole numbers. So all of the exponents in the expression have to be whole numbers. No variable is contained in the denominator. So if you have a fraction, that's okay to be a polynomial, but as long as the variable is not in the denominator. So a coefficient could be a fraction, the number in front, so you could have 1/2 x squared, but there can be no variable in the denominator. No variable is located under a radical. So you cannot have a variable underneath of a radical. It is okay to have a number, the coefficient under a radical, just not the variable. There can be no negatives or fractions contained in the exponent. And there can be no decimal exponents either. So last year you talked a lot, and even back in Algebra 1 you talked about the degree of a polynomial, you talked about the leading coefficient. So for example, is this, number 1, is this considered a polynomial function?
Yes.
Yes, it is. So if it is a polynomial, what is the degree? 3. Remember, it's always going to be the largest exponent for the variable. That's how you know what the degree of a polynomial is. What is the leading coefficient? The leading coefficient is 1. And what is your constant term? 1/2. Remember, the constant term is the term that has no variable with it. Look at number 2. First of all, is number 2 a polynomial? No, it is not. Why not? Because you have a 1/2 power. Because again, you have a fractional exponent. Okay? So take a look at 3. How about the plain old number 12? Do we consider just a number a polynomial? Yes, it is. And we have an actual special name for a polynomial with one term. Do you remember what we call it? A monomial. So this is a monomial. So what is the degree? So the question is, what is the degree? Well, then let me ask you this. If you're saying 12 is a degree of 1, what would the degree of 12x be? 1. So the question is, do you agree with me that if I write 12x to the 0, what is the value of x to the 0? 1. So actually, when you see a constant monomial, what's happening, you actually have a degree of 0. We're not going to write x to the 0 because we know it's equivalent to 1. What's my leading coefficient? My leading coefficient is just a 12. And the constant term is actually just 12. All right, so again, a constant by itself is indeed considered a polynomial. It's a degree of 0 polynomial. All right, so, and last year, and again, we've been spending a lot of time on factoring. Make sure you understand the difference if a question asks you for zeros versus factors. If you have a polynomial that's factored completely, it's easy to solve the equation, and we've been doing that. Remember, we can just take each factor and set it equal to 0. And then remember, the zeros are the same things graphically as your x-intercepts. So when you solve, you're actually finding the x-intercepts. So and when you do your solving, this is called a real solution or 0. Remember, we're not dealing with imaginary solutions anymore. The I's are gone. All we care about are the real solutions. Remember, you have a bunch of vocabulary words that can be used interchangeably for zeros. Zeros are the same thing as a solution, x-intercept, or root. I think I covered them all. Remember, so if I ask you to find the roots, I'm asking you to solve. If you want to find the x-intercepts, you're solving. The zeros, you do the same thing. So all of those words mean the same thing. Now, if R is a solution, x-intercept, or root, what do we call the quantity x minus R? That's not a root, that is a factor. So remember the difference. Make sure you're reading carefully. If I just want you to factor, you don't need to take the set of parentheses and set it equal to 0. All right? So take a look at this example. It's already factored for you. First of all, what are my factors? X plus 1 and my x minus 3. What are my zeros then? My zeros are going to be what? Negative 1 and 3. So everybody on the difference, because sometimes you read a problem, you're like, do I need to actually solve it? No. If it just says factor it, you leave it with the parentheses. You don't need to set each one equal to 0. All right, kind of sound familiar from what you did last year a little bit, maybe, hopefully. So if you factor an expression and it occurs more than once, we call this a repeated or double zero of f. So for example, if when you factor something, you end up with an x minus 3 to the second power, that's what we call a double root or a double zero. Something special happens if you have a double root or a repeated root graphically. If you have a zero, that's of what we call even multiplicity. So in other words, when we talk about multiplicity, a word you guys saw last year, that's just simply the power. That's the exponent for the factor. So at 2, 4, 6, 8, etc. If it's an even multiplicity, that's again the exponent for the factor. The sign of the graph does not change from one side to the other. The graph is just going to touch the x-axis at R. It doesn't actually cross over. So for example, if you've got a repeated root, let's say at 1, what happens with your graph, it kind of bounces off the x-axis. Notice it's not actually making that cross over the x-axis, it's just touching. You guys remember that from last year, the touching and crossing? If your zero is of odd multiplicity, the sign of f of x just changed from one side to the other. The graph will cross the x-axis at R. So again, if you've got an odd multiplicity, what will happen with your graph? It'll actually cross over. It makes that cross over the x-axis. Okay. And you guys should have talked about this last year, yes? Yes. Do you remember the relationship between the degree of a polynomial and the number of turning points? It's not the same. It's what? It's 1 less. So if I have a degree n, remember at most it's going to have n minus 1 turning points. Doesn't mean it's going to have exactly 1 less than a degree. It means it can't have any more. So if you've got a degree 3 polynomial, it could have no more than 2 turning points. Doesn't necessarily have to have 2. Yes, Chad?
That'd be like the one that you drew for B.
Yes. Mm-hmm. Yep. And behavior. So when you have an even degree polynomial function, so if you think about an x squared and x to the 4th and x to the 6th, if your leading coefficient is positive, then the graph goes up to the right and up to the left. So remember, any even degree polynomial function, you may have some bumps and turns in the middle, but both ends are going to face up. as long as the leading coefficient is positive. If your leading coefficient is negative, then what happens with both ends? Do you remember? They're both going to do what?
Down.
They both go down. So again, you may have bumps and turns in the middle, but again, the end behavior is both ends will go down. Oh, I guess I could have done my graphs down here, but too far away. So like I said, so again, bringing back the whole limit idea. Remember, we talked about the limit as x goes to infinity. This is another way of them asking you about end behavior. As x goes to infinity, what side of the graph I'm looking at? I'm looking at the right. And what's happening? It's going towards what? Infinity. When x approaches negative infinity, what side of the graph am I looking at? I'm looking at the left. And again, that's also going towards infinity. Remember, this is just another way of them asking you about end behavior. Again, if you have an even degree, leading coefficient is negative. Both ends go down. And the limit of an even degree polynomial function with a negative leading coefficient, what's happening with these limits? These limits are both going towards what? Negative infinity. Okay? So remember, anytime they ask you about limits going to positive infinity or negative infinity, this is just another way of them asking you about end behavior, which you guys talked about last year as well. Okay? Any questions about even degree polynomials? Odd degree. If the leading coefficient is positive, remember the end behaviors are different. So if it's an odd degree polynomial function with a leading coefficient that's positive, remember the graph is going to go up to the right and down to the left, like I sketched right here. If you have a negative leading coefficient, it's going to flip the end behavior. So what happens is it's now going to go down to the right and up to the left. Again, you may have bumps and turns in the middle, but the end behavior will be the same. So for example, odd degree, positive leading coefficient. What's happening as x goes to infinity? As x goes to infinity, what side of the graph am I looking at again? I'm looking at the right side, so it's going towards infinity. As x approaches negative infinity, remember I'm looking at the left, so it's going towards negative infinity. If you have an odd degree polynomial function and it's a negative leading coefficient, the behavior flips. So now what's happening as x goes to infinity, the end behavior, this is now going towards what? Negative infinity. And as x goes to negative infinity, again, remember I'm looking on the left, the behavior of the function, it's going towards infinity. Okay? So any questions on the behavior? So now, when I ask you to find the limits, like I mentioned, as x goes to infinity, I'm looking at the end behavior. So even though the graph isn't given to you, it's not specifically asking you to graph, you need to think in your mind what's happening graphically. So what kind of polynomial is 4x squared minus 6x plus 2? This is odd or even? Even. Leading coefficient is positive. So you don't need to give an exact sketch. Just think in your mind, what does an even degree polynomial function look like whose leading coefficient is positive? So as x approaches infinity, I'm looking at the right-hand side of this graph. So what's the behavior of this particular function as x goes to infinity? This is going towards what? Infinity. Remember, anytime they ask you about limits going to infinity, it's an end behavior question. So then what's the answer to part B also going to be? Instead of looking on the right-hand side like I did in A, I'm going to look at the left. So what's the behavior on the left-hand side? This is also going towards what? Infinity. Okay? So when they ask you about limits going to infinity, the question's not going to say to graph. What you have to understand in your mind is you've got to remember what the behavior of these functions look like. So now let's take a look at C. The limit is x goes to negative infinity. What side of the behavior am I looking at, the right or left? Left. So now take a look at this polynomial function. Is it an odd or even degree? Odd. So I know it's an odd degree function. What's happening to my leading coefficient? The leading coefficient is negative. So think in your mind, what does an odd degree polynomial function look like whose leading coefficient is negative? It looks something like this. So what's the behavior of this graph that's going towards what? Positive infinity. Because again, you're looking on the left. So anytime they ask you about limits going to infinity, they're talking about end behavior, so you need to think in your mind what's happening with the graph. Do a rough sketch or think in your mind what it looks like. So D and E, I've already given you the graph, so you go ahead and answer the question for D and E. And then part E, you've got the right-hand side is negative infinity, and the left-hand side is towards positive infinity. So any questions, guys, on finding limits as you go to infinity of polynomial functions? Because that's really what we're doing, is finding the limits as you're going to infinity of polynomials. It all depends upon the degree. It all depends upon whether the leading coefficient is positive or negative, what's happening at the ends. All right, so now to kind of put this together, let's do some sketching. So let's take a look at how we can do some sketches of polynomial functions. So first of all, they've already done the factoring for you. So when you go to sketch a graph, first of all, like I mentioned, the limit is x goes to positive and negative infinity. This is telling you the end behavior, so you know how to sketch the graph. Both ends go up, one side goes down, the other one goes up. So first of all, to determine your end behavior, you've got to figure out the degree. So the degree is not as obvious if you have already got the polynomial factored for you. So do you remember from last year, if it's already factored, how can you figure out the degree of this polynomial? What do you do with all these multiplicities? You're going to do what? Add them together. So 4 plus 3, by the way, what's the power written here for x minus 1? 1. So you just add all those multiplicities together. So 4 plus 3 plus 1 is going to give me an 8. So I've got an 8th degree polynomial function. So is 8 an even or odd number? Even. So I know I have an even degree polynomial function. So I know both ends will go up, both ends will go down. So now the question is, what's happening with the leading coefficient? Is the leading coefficient a positive number or a negative number? Positive. Notice all the x's are positive. There's no negative x here. So my leading coefficient is positive. So what's going to happen with the end behavior of a even degree polynomial function where the leading coefficient is positive? They're both going to go up. So the limit is x goes to positive infinity and negative infinity are both infinity. So I know when I get finished constructing my graph, the left and right hand side of this graph better be pointing up. Okay? Are we good so far? So now let's find the x-intercepts and state if it's going to cross or touch at each x-intercept. So they've already factored it for you. X-intercepts, remember, are the same thing as the solutions. So all I need to do is take one of my factors and set it equal to 0. So then what's one x-intercept going to be? X equals what? 2. Now, it's an even multiplicity. So if it's even, what's going to happen at the x-intercept x equals 2? Is it going to touch or is it going to cross? Touch. So I know it's going to touch. I'm just going to write a T there. My other factor is x plus 1. So what's another x-intercept going to be? X equals what? Negative 1. So because it's an odd degree multiplicity, is it going to cross or touch? Cross. Now, when you have a multiplicity that's odd and it's greater than 1, I like to say it crosses with a kink. Did they use a different word last year? It doesn't make a straight crossover. In other words, it kind of crosses. Think about the x to the third graph for a minute. Oh, they use the word wiggle? So at x to the third, if you think about, that's what I mean crossing with a kink. Versus having a graph that just goes straight through, just a straight line. So they use the word wiggle. I always use the word kink. It crosses with a kink. So anytime it's an odd multiplicity and it's greater than 1, it goes with a kink. What's another x-intercept? Another x-intercept is going to be what? What's another x-intercept going to be? X equals 1. Now this has an odd multiplicity of 1. This is going to make a straight crossover like a line. Okay? How do you find y-intercepts? Plug in 0 for x. Remember, anytime you want to find a y-intercept, you plug in 0 for x. Doesn't matter what kind of function you have, but anytime you want to find a y-intercept, you always plug in 0 for x. So y is going to be equal to 0 minus 2 to the 4th times 0 plus 1 times 0 minus 1. So this will tell you what the y-intercept is going to be. You found your x-intercepts by setting each of your factors equal to 0. Now to finish the graph, we're going to find the y-intercept. So what's 0 minus 2? That's going to be negative 2 to the 4th power. So what's negative 2 to the 4th power? Times 1 times negative 1. So negative 2 to the 4th is going to give you a positive 16 times negative 1. So it's going to be what? Negative 16. Remember, the y-intercept is a point. You write it as a point. I'm sorry? Yeah, but it's still 1. 1 to any power is still going to be 1. So are we good on how to find the y-intercept? What's the maximum number of turning points to this graph? 7. Remember, you take the degree minus 1. Okay. So now let's go ahead and let's start constructing the graph. So first of all, always label your x and y axis. So I have an x-intercept at 2. I've got an x-intercept at negative 1. And I'm going to have another x-intercept at 1. Some of these y-intercepts are going to get really, really large or really, really small. I certainly don't expect you to count down to negative 100 if you end up with a y-intercept of negative 100. Just go as far as you can and label this as negative 16. So that's going to show where it crosses. Remind me again what's happening with the ends. Both ends are going to do what? Both ends are going to go up. So remember, what's going to happen at negative 1? I'm going to cross with a kink. Or a wiggle.
How do you know if it's a linear?
It's got to be an odd number greater than 1. So then I'm going to cross the y-axis. What happens at x equals 1? I'm just going to cross at a straight line. Now this is where our graphs may be differentiate from one graph to another. We don't know how high or how low, but I do know this graph is going to have to turn somewhere between 1 and 2. But until you get to calculus, you're not going to be able to find those points exactly, those turning points. So you just have to turn. We know it's going to come down, it's going to cross the x-axis at 2, and then it's going to come back up. Okay? So there's a sketch of that polynomial. What we're going to do next class is we'll use the calculators to find out exactly what this point is. But right now, like I said, until you get to calculus, you don't know the math, you don't know derivatives yet to find that point. You need to know calculus. Well, we can use it on our calculators. 7 what? Yeah, maximum numbers, degree minus 1. Remember, it says maximum. You don't have to have 7. Okay? Yes. I heard of Miss Bernie. Yeah.
If the, like, for one of the
Any questions on finding the pieces to this polynomial? So these are the things I expect you, we're going to get into later on, factoring these particular polynomials, which I know you did last year. Sometimes you need that synthetic division, all that stuff. That's coming up later on. For right now, I want to make sure you're comfortable with what the graph looks like when it's in factored form. So we'll get into the factoring later on. So any questions on finding any of these pieces of information?
Do odd numbers sit at top?
Yes. Odd powers for the factor. So the only odd power you have for the factor is 3. So the only one that's going to cross is the x-intercept at -4. Right. So it all depends upon the power for your factor. That's what's going to dictate whether or not it's crossing or touching. So then I know this is going to be down here at -64. There's my y-intercept. X equals -1. I know it's going to touch. x equals 1 is also going to touch, and then x equals -4, it's going to cross. So if it's an odd degree polynomial, leading coefficient is negative, remember the left side's going to go towards infinity, the right side will go down towards negative infinity. So I know it's going to behave like this. At -4, I know it's going to cross with a kink. Again, we do not know how low this one point's going to go, but it's going to have to come up. It's going to have to touch at -1. It's going to have to come back down, cross the y-axis at -64, come back up to x equals 1, touch, and then go down to negative infinity. So that's what the sketch of this graph is going to look like. Again, the variations in our graph will occur as to what's happening between -4 and -1. All right? So any questions on sketching the polynomial functions? Okay. All right.